spell out its own name so it can read and write. So our conclusion, so like I said in the introduction, the environment of the Luzerne area is in danger because of the mining that used to be. Right? There's pollution that's being deposited in places like the Susquehanna River, and it's being gathered by this water. And the important part is how this water is going into these mines and picking up these minerals, and that's what our robot hopes to solve. So in theory, they should be able to go through surface fractures, map the geometry, so then people like Dr. Whitman can then do hydraulic analysis on how the water is flowing in and help come up with a solution to stop it.
So these are the references for all the images we used in our presentation.
And we'd like to end with some special acknowledgments. So first, Dr. Whitman with approaching us with the problem and the idea, Dr. Zhu for being our advisor and helping with the robotics, Dr. Young for helping with some of the mathematics which went into the software, and finally Dr. Mu for help with 3D printing and pointing us to the right material for the job.
Any questions?
You mentioned this has, well, first off, well done, very well done. That's rare for me. You mentioned this has wireless communication. Can you expand on that? What kind of communication protocols is it using?
We're just using 2.4 gigahertz radio communication.
Yeah, so here's the thing. We're in a big concrete building, and I don't got no cell phone
Right,
reception.
so right now, mainly we're using radio so we can test the controls and make sure everything's working. But we are looking into different options because we know that radio will not pass through sheets of rock.
Okay, yeah, that might be something to consider for
Yeah.
your rough terrain tests. It's
Right.
just kind of, what is the range of this thing if it gets too deep? Is
Yep.
it gonna
So that's something we're going to be testing.
run away from us? Yeah. Yeah, very well done. What do you define as basic movement tests, by the way?
Like I said, that would be including moving side to side, forward and backwards, forward and backwards.
One other question, what kind of servo motors are you using? Are these geared servo motors? Do you have some kind of over torque protection in them?
Yeah, they're geared. The specific models are D89 MW. And for torque, we don't really have torque protection, but we have current limited within the geometry.
Okay. Yeah, something interesting I'd like to see that I believe in assets explored is the idea of what if one of my motors, or if you're a Mars rover, one of my wheels breaks, how can I compensate for that?
Yeah, we don't have anything like that, but it's something to think about.
Get back on the communications piece. How deep into the ground do you think a radio wave can travel?
Not too far.
Yeah, and so the concern that I have is you're going to get this thing down into a fracture, you're going to lose communication, you're going to lose it.
Right.
I'm assuming that you're going to be tethered?
Right. We got on the back, we have holes, so we have a
So
paracord.
you're going to be tethered.
Yeah.
So why don't you build into the tether wired communication so this thing's fly-by-wire as opposed to wireless?
Because we don't really understand how it moves there, so we don't want the wires to get caught and broken.
Again, it's a part of the design.
Right.
The tether, okay, whatever that tether is going to be, the wire could be in the center of the tether. You could do something like that.
Ideally, eventually, probably not during this year or this semester, the robot would be able to move on its own and function on its own. So if it's going to search and rescue places where you don't want people there, you just want to send a fleet of robots, there won't even be tethers attached. So we want it to be completely self-contained so it can function on its own.
The final thing is the device that you have there. I know it's prototyping that, but it's all the electronics is open to the air. When this thing goes underground, there's moisture underground and
Yep.
so on, which is going to affect the electronics. I'm assuming that this thing is going to have some sort of flexible sheathing on the outside.
Yeah, so we've been talking about this since we started the project. We have to come up with some type of way to waterproof it. We have gotten different types of plastic tubing to try to slide it into, but it ended up not being what we needed. And so our latest idea was to try to put it in fire hose and seal the ends off, with the front end being some type of clear plastic so we could still gather data, but the rear just being completely closed so it's watertight.
Do some research into animatronics. You're going to find some materials, that they've used, and this has other applications besides the noble thing of going down and looking at the mines. You guys could have a job in Disney animatronics.
Okay, we'll look into it.
I loved it.
Thank you.
Very non-technical question. You have a lot over these years.
Yep.
What was it that in September
Yeah.
and starting now.
So, the last year, right, the first year was making this first prototype. And then over the summer, we started the groundwork of making the second prototype, and I was mainly getting all the components that we would need. So a lot of this semester was actually designing the second prototype, making it functional, and the construction, and then moving forward with the testing.
So going from wired to wireless.
Yeah. Well, the first one, they're both wireless. The main jump between the first and the second was including batteries. Because the first one, you need an external power source.
One question, how did you define the length of the prototype? Just wondering because you can find a fracture with huge length or small fractures or porous medium. So could you provide more information about that?
Say it again? Sorry.
How did you design the length of your prototype?
How long is it?
Yes, so how was the process in order to decide the length of that?
The main process was getting enough degrees of freedom for reliable movement. So our first one had 10 motors. We decided to upgrade to 12. And we tried to get the length of each segment to be as short as possible to still fit the motor and the battery. So the segment design kind of regulated the length.
Okay. Thank you very much. Okay, next we have our at-home gas turbine. They're our last thing before our quick break.
Yeah, I'll grab that. Got it.
All right, good morning, everyone. My name is Patrick Seeley.
I'm Andrew Lamb.
And our project is the at-home GT, final presentation for 2022.
A little bit of an introduction about what we are. We decided to create a project that uses knowledge that's acquired in the last 3 years. The topic concerning internal combustion was selected due to our love for thermodynamics, fluid mechanics, and heat transfer, knowing that it would provide a challenge to test our skills. A little bit of a back statement to why we wanted to choose this is every year 12 to 15 million cars are junked. A lot of the times these cars have a turbocharger in it that could be used for any sort of purpose.
So a turbocharger is a purely mechanical device that is used to boost the output power of a combustion engine. So a turbocharger has two separate housings. It has the compressor and then the turbine. So a turbocharger works by pulling in air through the inducer and sending that air to wherever the combustion will happen. Once the combustion happens, it will send the exhaust to the turbine side where it will spin the turbine wheel, and the turbine wheel shaft is also connected to the compressor shaft. So when the exhaust spins the turbine wheel, the compressor wheel will also spin, pulling in more air and the possible beating again.
So as Andrew just mentioned, now that we know how a turbo works, pretty much a like gas turbine functions the same way, except all that it would need besides a turbocharger is a combustion chamber. So essentially, if we could build a combustion chamber on this turbocharger, we could potentially have a gas turbine engine. So with all of these junk turbos, why not use it for this purpose? Not only would this be able to compete with similar sized gasoline engines, but also it would be a really unique twist power source for like enthusiasts who would like to build their own engines at home. And finally, it would be a very, very good opportunity for the recycling industry. We estimated there would be the 3 to 4 million turbos junked every single year. And then finally, the scope of our project, these turbos, people have built them in the past. but it was always a trial and error for the most part. They didn't really have any good answers or numbers or values. So our goal is to make a very efficient, reliable, and cheap one that can be very easily done and made by future users, giving excellent results.
A little bit about our requirements. It's about $750 per unit. Luckily, a lot of them scrap metals that we can utilize for finished stay on our budget. The size of the bolt is going to be no more than 150 pounds. Power output, you must produce at least 13 horsepower to compete in the industry. Should run for about 500 hours of max power. And safety is a priority in engineering, so it must be safe under normal operating conditions.
So here we have all the main components of our system, and it shows here's the diagram that shows our process. In the red, we have our fuel coming from our propane tank into the combustion chamber. We have in the yellow our battery powering our spark plug for the initial combustion. In the blue, we have the process of the air going through the compressor and turbocharger into the combustion chamber and then out as exhaust. And then we have in the purple showing our lubrication and cooling system using oil. And here we have the design of our combustion chamber, showing kind of what's going on inside. We have two tubes that kind of make our whole combustion chamber. We have the outer tube, which is our outer shell, and then we have the inner tube with the holes in it, which is our flame tube. In between the outer shell and the flame tube, we have the compressed air coming from the turbocharger, which will circulate around the flame tube to make sure and allow for air to flow in through the holes. You can see we have 3 stages of holes. We have the right and the left, we have the primary, in the middle, we have the secondary, and on the right we have the tertiary. For the primary, it is primarily for mixing with the fuel, and you can see the fuel is coming from the end cap on the left, and then the initial spark is for the spark plug is for the initial combustion, and as only for the initial combustion is the spark plug needed. So after that, only a steady flow of fuel and air from the primary holes is needed to keep the flame going. The secondary set of holes is to help burn any excess fuel that doesn't burn completely in the primary zone, and also start the cooling process of the flame so that it does not burn too high, does not burn at too high of a temperature. And the tertiary holes is to complete that process to make sure that the turbine and the turbocharger are all completely safe from too high of heat. So now that we have our turbocharger combustion chamber described, these are some main calculations for the combustion chamber. The first calculation you see there is determining our mass flow rate of air, and then